Okay, let's get started. So first of all, any questions for the homework? So do you see the solution already? Yeah, so yeah, just let me know. After seeing the video, just let me know if you have any other questions or not. Okay, yeah, the video was recorded a long time ago. Yeah, so yeah, I don't remember what I reported there. So if I say anything wrong, just let me know. Okay, so normally we cannot find solution online. So I think there is a solution. It's a like partial solution online, but I'm not sure. I'm pretty sure that there are some mistakes there. Okay, I don't know. I don't recall where are the mistakes exactly, but there's no official solution of this homework. So yeah, when I did it, when I put the solutions, I did it on my own. So it is possible that I made some mistake, right? So if you disagree, then just let me know. Okay, great. Yeah, let's review what we covered in our previous lecture. So we're still in our chapter 4, right? Remember that we go to chapter 5 a little bit, and then we go back to chapter 4. So after that, we're going to going back to chapter 5. Okay, and so in the last lecture we talked about Markov chain, right? We discussed a lot of details for Markov chain, and then we start talking about the entropy rate. All right, so yeah, this is a definition again. So it's just a brief review, right? So from the beginning. So basically, we model a source with memory as a random process, right? So and this is a definition of the stationary process. Okay, so basically it means that the distribution of the sequence of the random variables or the random process, it does not depend on time, right? So if we shift it a little bit, then the distribution is exactly the same. Then it's called stationary, okay, or strict stationary. So, and then we define Markov chain, right? The definition of Markov chain is quite easy, right? So basically, it basically means that given the current state, right, and the next state does not depend on the past, right? So it sounds very easy, but if you think it more, so it's not that trivial to understand. We're probably going to see one example to indicate that. So this definition is not trivial. Okay, and then we say a Markov source. If an information source follows a Markov chain, then it is a Markov source. Okay. And in our class, we'll focus on the stationary process and the Markov process or Markov source. All right, and so this is the definition of the transition probability matrix, right? So here we consider the stationary Markov source, right? So basically, the transition does not depend on time, right? Then so let's say, so we have let's denote the total set as from 1 to n, right? And then, so we have this short notation here, right? PRS, which basically means that, so R is the current state, right? And S is the next state, okay? So R, is a current state and S is the next state. All right, and if we write in this way, so of course you can write in the other way, right, if you like, but doesn't matter. So if you write in this way, then this PRS form a matrix, right? So we call that stochastic matrix. The reason we do that, we call that is that the summation of each row equals to 1, okay? And if the summation of each column also equals to 1, it's called doubly stochastic, right? But here we just consider the stochastic matrix, okay? And then we have the propagation equation. So basically it means that, so let's say this is the probability distribution of the state I minus 1, of the state I minus 1, and then the next state would be this guy multiplied this guy, right? And this, because this follows the total probability formula, and you can write it out and see whether it's true or not. Okay, and then so if we keep doing this, okay, and hopefully eventually, so this P I minus 1 and P will become the same, right? It means that, so the Markov chain will become stable, right? Right? So it will follow just one distribution, right? And then how to solve this stationary distribution is that we just let this pi equals to pi times p, right? And solve this equation, then we get the stationary distribution, right? How to solve it, right? We just move this side to the other side, right? And then do a left eigenvalue decomposition, right? So basically the pi is the eigenvector, the left eigenvector corresponding to the 0 eigenvalue, okay? And then you get pi here, okay? It's just linear algebra. Okay, and then we say, So then we want to see under what kind of condition the Markov chain has a stationary distribution, right? The condition are twofold. Number one is irreducible. Basically, so it means that in the Markov chain, you can get from one state to any other state with positive probability, right? Then it's called irreducible. And then it's aperiodic. Basically means that the period of the Markov chain is 1, right? And then if satisfy these two conditions, then we can say the Markov chain will achieve a stationary distribution. Okay, basically means the function will have a solution, right? Okay, and then we have a corollary here. So let's say if a finite state irreducible and aperiodic Markov chain initialized with a stationary distribution, then of course the Markov chain will be a stationary process, right? And for any arbitrary this Markov chain that is irreducible and aperiodic, you can say asymptotically, so it will become a stationary distribution, a stationary Markov chain, right? Not exactly, but asymptotically, right? As n goes to infinity. Okay, so yeah, this is the Markov chain, and then so we covered entropy rate. The title here is wrong, so I should write entropy rate here. So basically the idea of entropy rate is that, okay, so now we have a source with memory, right? So yeah, we're still under this big topic, right? So the source with memory, and then how can we kind of reproduce our previous coding result, right? Before we consider IID source, right? And then we say, so the number of bits per symbol, the minimum number of bits per symbol is given by entropy, right? So yeah, we prove, we have complicated proof on that. Right, but now let's say if we have a source with memory, and then we want to basically duplicate what we got before, right? And how can we do that, right? And so this is the way that how we can do this. So basically we define the entropy rate, which is average of the joint entropy. This cannot make sense, right? So at least intuitively, right? So now we have an entropy of a big vector here, right? And then what is the number of bits we need to code each symbol, right? So that should be this guy divided by n, then we'll just let n goes to infinity, right? So it's not rigorous, but at least this should be that, right? Intuitively, okay? So and then we focus on more kind of computation side on how to compute the entropy rate, right? Because evaluating this is almost impossible, right? Yeah, because we have like the length is n, and n has to go to infinity. Right? We have infinite, so many number of terms there, right? So computing that is hard. So we focus on how to compute that first, right? And then we're going to show actually it is true that we need this number of bits to code each symbol. All right, and then we look at some special cases. The first one is DMS, which is RID, random process, okay? And in this case, this guy can be broken down, right? And so it's easy to see that entropy rate and entropy are the same, okay? And then consider another a little bit more complicated case, and that is when the sequence is still independent but not identically distributed. Therefore, the key part is that we can still break those down, right? Using a summation here. So that's basically the entropy rate, right? So those two are two simple cases that are easy to see, right? Okay, so but what is not trivial is a general case, right? So in general, so we can show this theorem, the entropy rate basically equals to this. Okay, it seems very non-trivial, right? Because this is a conditional entropy. Right? This is the entropy that given all the past random variable, and what is the entropy of the current random variable, right? So basically, if like n goes to infinity, then this guy will converge to the entropy rate, right? And we're going to finish the proof of that today. Right, so EEL6532. Today is our lecture number 16. Yeah, today we're going to finish talking about the entropy rate. And then we'll talk about the hidden Markov process. So which is like one step further from the Markov process. Okay, and probably we don't have time to talk about anything else, right? But if we have time, or in the next lecture, we're going to talk about the last part here, so which is the AEP for stationary ergodic process. Okay, yeah, we'll talk about what is ergodic process later. All right, so let's continue our proof, right? So yeah, let's recall our theorem. So theorem is that for a stationary random process xi, right? And then, so we can show that our entropy rate is given by this limit. Right, and in our last lecture, we proved the first part, right? The first part is that, so basically, we show this guy is less than or equal to this guy, right? So basically, it means that, so this function is monotonically non-increasing respect to n, right? So it means that, so this guy is kind of decreasing, right? Non-increasing, right? So monotonically non-increasing. Okay, and together with the fact that, so this guy is bigger than or equal to 0, meaning that it has a lower bound, right? Then it means that the limit exists, right? So by the way, on the other hand, right? So let's say if we have a sequence that is monotonically increasing or non-decreasing, and then it has an upper bound, we can also conclude the same, right? So it will have a limit. The limit will exist, right? So this is the first step, right? So if you don't recall, just look at the lecture notes last time in our last lecture, and then you'll see the details. Okay, yeah, this is the first step, right? So next step, we're going to show that, okay, actually, and so the limit of this guy and this guy will be the same, okay? So in other words, second step. So in other words, so basically we know that, so the definition of this is equal to this, right? Okay, so basically what we need to show is basically this and this will be the same, right? Okay, how can we do that? Okay, so now let's do some manipulation here. So when you want to, the only thing now we can do is to manipulate this and relay this and that. That's it, right? And how to relay these two quantities? Yeah, say it loud. Yeah, you should know that, right? You did your homework, hopefully. Yes, 18 hours. So 20 is the deadline, right? Yeah, what should they do? Chain rule. Exactly, right? So this is the only thing we learned, right? We just do the chain rule, and also here is a conditional entropy, right? That's the only thing we do. Okay, yeah, let's try to expand it. So 1 over n doesn't matter, right? Just a scaling factor, right? And then we expand it using our chain rule, right? So hopefully you remember it. And then, so this and this, they are almost identical, right? What are the differences? So here we have like n terms, and here we only have one term, which is the last term, right? So now it's kind of tricky. So then, any idea? So basically, we know when n goes to infinity, this guy and this guy are always the same, right? Therefore, when n goes to infinity, so this guy will definitely go to the entropy rate, right? But now I want to show when this guy goes to infinity, it also goes to entropy rate. So basically it means that, so when it goes to infinity, this guy and this guy are identical. Does that look familiar to any of you? No, it doesn't matter, just a theorem. So let me introduce the theorem here. So basically, we have a theorem, it's called Casaro mean. So we have a lemma. Casaro mean. So who heard of this lemma? So it's a typical lemma in analysis. So basically, it means that if we have one sequence, an, right? So that's a sequence, okay? So indexed by n, right? We say if this guy goes to b as n goes to infinity, right? Then, so bn will also goes to b with the definition of bn is probably you can guess that already, right? Is the average of an. That makes sense, right? So now our theorem is almost for free, right? So now we just consider this guy as our an, okay? And the whole thing, the average, so that's our bn, right? So now we say, okay, if an goes to bn, then this guy will go to bn, right? Does that work? Does that work? Why? Kind of reverse, right? I mean, if this guy goes to b, and then the entire thing goes to b, right? But what we want is that the entire thing goes to b, and an goes to b, something like that, right? That reversed, or no? Or how can we conclude our proof? Right? Yeah, following the math is not hard, right? But what's the idea here? Yeah, we need to consider this guy, right? So we have the first step, right? So this is the second step. So now, yeah, let's see how we can use the first step and second step to conclude our theorem, right? So basically, the thing is like this. So now let's consider an, right? Because we have to use an first, right? Now use the bn. So this is our an, the limit of our an, right? So we know if the an will converge to b, right? So what is b? So we know this guy has a limit, right, from the first step here, right? So this guy will converge, right? Converge from the top, right? So it's a decreasing function or non-increasing function, non-increasing function. So then we say, okay, it will converge to h, for example, right? We know that's converge, and then we just assume, okay, the number is h, right? So then an converges, right? Therefore, we can conclude that an will equals to bn, right? Bn. Right, this is bn, okay? So an converges and an equals to bn, right? And this guy will be, it's nothing but this, right? So it's by chain rule, so this guy equal to this, right? And then this guy equals to entropy rate. And then we're good. Okay, then we can say that, okay, now the entropy rate equals to this. Right? Is the logic clear? Right? We do need the first step, right? That's why we need, yeah, from the second step, we cannot conclude that. Okay, it's reversed. So we do need the first step, right? So this is tricky proof. Any questions? Any questions? Okay, yeah, you may think it twice, right, when you get home. Okay, so now we have an observation from our result, right? So, you know, from here, I think the computation will be easier, right? But actually, we have a very important observation from this theorem. So let's see that. Know that. Okay, so this guy. Okay, again, so let's expand it a little bit. Right. So because it's a non-increasing, kind of decreasing function, right? We can conclude that this guy is bigger than or equal to the last term, right? Right, because last term is the smallest. Okay, and what does that tell you? Yeah, this is kind of interesting, right? And for this guy, we can somehow understand that. So we treat all the n random variables all together as a block, right? As I told you before, right? We can, treat all this n random variable as a whole random variable, okay, and do whatever we do, okay? So basically, we're going to treat this n random variable all together. So you can, I mean, if we do that and then use what we learned before, we can conclude that, okay, so this is pretty much the smallest number of bits we need, right? So this is the result of block coding. So we're going to talk about that later in very detail, how to do a block coding. Block coding basically means that it's a fixed length coding, right? So fixed length, I mean, it's fixed length to probably either to fixed length or variable length, doesn't matter. But the key is that, okay, we treat, each block as a whole and then map that to another code word, right? That's a block coding. That makes sense, right? So many, practical codes are block coding. Yeah, like the LDPC we use in 5G and so on, right? So before in 3G, so who heard of 3G? Yeah, probably you were born, right? So you were born like when? 2000 something? Yeah, that's right, when the 3G is still in use. Yeah, in 3G we used a code called turbo code, okay? So that code is a convolutional code, that's not block code. So it's not, if it's not block code, what kind of code is that? Look at this. So can you get any intuition from here? Right, it basically means that we know the past n-1 symbols, and then we're going to encode the next one, right? So if we think this kind of entropy, conditional entropy, is like we know the past, and then how many bits we need to encode the next, right, intuitively. Does that make sense? Right, so this is not block code, right, because we do actually, yeah, let's say we consider if n is very large, we use all the past information to kind of encode the next one, and then next one, and then next one, and so on, right? So this is called sequential coding. Many practical codes are sequential coding, okay? So now from these two quantity, you can see, okay, one represents block code, or the optimal rate of the block code, and the other one is sequential code, okay? So although when n goes to infinity, they are the same, right? We just proved that. That's a theorem, right? When n goes to infinity, they're the same. But in practice, n is never infinity, right? So when n is not infinity, which one is better? Sequential, right? Because sequential is smaller, right? So we're doing compression, smaller the better, right? So basically, this one is better. Okay, so remember we have a condition, so it's for finite n. For finite n, sequential code can be better than block code, right? It doesn't mean sequential code is always better than block code, right? If you design in the correct way, right? So this is a limit, right? So if you try your best, then sequential code will be better than block code. From the pure rate perspective, right? We don't consider complexity and so on, okay? So that's one important implication from our theorem, okay? Any questions? Okay, no questions, so let's continue. So now, so for this theorem, it works for any stationary random process, right? So now let's focus on Markov process and see what will happen, okay? So we're going to compute the entropy rate of Markov process, Markov sources. Okay, so we consider a Markov source. So that is stationary Markov source. Okay, and we assume that start with stationary distribution, right? That's how it becomes stationary. So with a stationary distribution, pi, okay? And then let's compute the entropy rate, okay? This is a computation of the entropy rate. So using the theorem, so we can compute. This is given by this. Yeah, be careful for the indices. Okay, so now you can see that for Markov source, then using this formula is very easy to compute, right? So from here, we can see clearly, we use a Markovian property. Use a Markovian property. So this guy will only depends on the previous state, right? n-1. Okay, we can ignore everything else because it's a Markov. Okay, and then because it's stationary, so this n doesn't matter anymore, right? So we can just simplify it by using x2 given x1, right? So this is stationary. Okay, great, very good. So now we can compute that explicitly, right? So just compute the conditional entropy here. So remember, so this guy is a starting point, right? And we know the distribution of the starting point, right? So it's stationary distribution. Stationary distribution, right? So that is pi. Okay. And then given by that, so we'll just compute. Oh, by the way, so this guy, there's no n anymore, right? So this guy will just give equal to this, right? There's no n anymore, so let's compute it. So basically now we just use the formula of the conditional entropy, right? Hopefully you still remember it. Do you?
Off the top of my head now.
Really? Yeah, come on. So it's very easy to remember it, right? So we say x1, x2 log 1 given a p probability x2 given x1, right? So that's the definition, right? So the tricky part is here. So the average has to be over the joint distribution, right, instead of conditional distribution. Okay, and then we can break it a little bit, right? So basically that equals to x1 in x, p x1, and then x2 in x, p x2 given x1, log 1 over p x2 given x1. Okay, very good. And now recall our notation before, right? So notation is that, so this guy is pi. Okay, so let's say if we say, remember this notation, so it's p r s, right? Let's say given r and, or we say, so this is equal to s given r equal to that. Okay, and this is PRS. Okay, and given that, so here should be x1 is r, right? So it's pi r. Okay, we just use our, the notation to substitute the symbols here, and then we can write this guy as the summation of r from 1 to capital M, right? We have, so that's all of our state, pi r multiply s from 1 to m, PRS log 1 over PRS. Okay, and then if you look at that carefully, so what is that? PRS log 1 over PRS. So this is for fixed r, right? And then remember our matrix. Okay, remember this matrix P. So basically, so all of them corresponding to one row or the rth row, right? and then clearly that's the entropy, right? So basically we can understand that, so this is the average, this is the, not average, this is the entropy of each row in P. Okay, so entropy of each row, right? Because each row is a probability distribution, right? And the meaning of this guy means average, right? The whole thing basically means the average entropy of each row, right? Does that make sense? Okay, so now for Markov stationary Markov process, so you know how to compute the entropy rate, right? You just compute the entropy of each row in the transition probability matrix, and then just average them. That's it. Okay, so that's the Markov source. Okay, any questions? Yes.
Is it ever useful? Is this kind of, it's kind of related, but is it ever useful to parameterize just distributions to solve this type of stuff?
Yes, of course, but it depends on what kind of a parameter, your parameter. Right? If you consider, every PR is a parameter, then, of course. Yeah, but in practice, in machine learning, for example, we always, model this probability distribution. We parameterize it, right? So softmax, for example, right? Yeah, I think, I think in practice we do some parameterization. Okay, great. Any other question? Okay, so if no other question, let's consider a second topic, so which is a hidden Markov process. Yeah, we'll talk very briefly about it, and then we are now going to talk about the official hidden Markov process. We'll only talk about one simple example. Okay, who heard of it? Okay, so didn't learn that anywhere in your signal processing or whatever class? Okay, yeah, so probably nowadays they should talk about that. So, when I was in my grad school, so this is a very important topic because, so this is a key for the speech processing. Okay, so in speech processing, we always use that. Okay, hidden Markov process. So one example application is speech signal processing, right? And why we need this kind of thing, right? So basically, so in practice, so we cannot observe, normally, in many cases, we cannot observe the state of a Markov chain, but we can observe a function of the state of a Markov chain. Okay, so yeah, let's write it down what I mean by that. So basically, consider this xi be a Markov chain, okay, and we'll consider another set of random variables, yi. Okay, that is a random process. That is a random process defined by, for simplicity, we just consider yn equals to a deterministic function of xn, right? So this is a deterministic function. Okay, so, but it could be a random distribution, right? So it could be, so this also works for this. So probability of yn given xn, right? So if we have this, so that's the official definition of a hidden Markov process. Okay, but for simplicity, we just assume we have a deterministic function here. Okay, so now here's the tricky part. So basically now we have state 1 from state 2, from state 3, and so on. So from state n and continue. So this is a Markov chain, right? X is a Markov chain. So now So from x1, we get y1, right? y1 is a pure function of x1. y2 is a pure function of x2. And here, this is y3. This is yn, and so on. Okay? So now the question is that, okay, so y is observable. So we know y, okay? But we don't know x. Of course, by knowing y, you can infer some information about x, right? But the problem is that phi may not be like one-to-one mapping, right? Phi is arbitrary. Therefore, let me ask this question. In general, is the random process of y a Markov process? Is it? In general, I mean. Of course, you can have example that. Yeah, who think it should still be a Markov process? Very good. Yeah, that's intuition, right? Why not? It's a one-to-one, no, not one-to-one mapping, but it's a deterministic function, right? So, yeah, for the for the ones who do not think it's a Markov process, why? Or do you have any reason? Or just guess? Logically, it is not, right? If it is, then why do I want to talk about that, right? So everything we learned before holds, right? The answer is no. Why may not be? But why is that? Yeah, think in this way, right? So if x and y is one-to-one mapping, then of course, right? So the problem is that when x to y is not a one-to-one mapping. Right, I see some nodding there.
It's a deterministic function.
What?
It's a deterministic function from x1 to y1.
Yes. Yes.
So so for example, like if it's Markov chain, like given y2, y1 and y3 should be independent. But yeah, if it is not one-to-one mapping, like y1 and y3 can like have like same value but different x, so like it's not Markov chain.
I think the chain of thought is correct. Right. Yeah, probably. Yeah, let me give it. It's not. Yeah, we can just cook up a very simple example, and you can work it out a little bit. Let's say, for example, we have Markov chain like this. Yeah, I was thinking this before my class, right? And I just think, okay, so probably I should cook up an example, right? Because it's not obvious. We can consider this kind of Markov chain, right? From so this is x, of course, right? x1, x2, x3. Okay, let's say x3 always go back to itself, right? This is a simple Markov chain, right? So they're all x. Yeah, I should write. Let me do it this way. So let's say it's 1, 2, 3 state. Okay, yeah, so it's not x1, just x. So those are all x. So these are the Markov chain for x, right? So now how about I define y as follows, right? So let's say y equals to 0 when x equals to 0. Oh, sorry, x equals to 1. And y equals to 1 when x equals to 2 or 3. Right, so that follows our intuition, right? So it's not a one-to-one mapping anymore, right? So x2, 3 map to y equals to 1, right? So in this case, so we can see that if we want to compute this probability, yi plus 1 given yi, right? And now let's say let's assume the interesting case, right? So yeah, y equals to 0 is not very interesting, but y equals to 1 is very interesting. Right, when y equals to 1, then we have two options for x, right? So this basically means that xi equals to either 2 or 3. Okay? You see the problem? Right, so now we can see that, okay, so now given I equals to 1, x equals to 2 or 3, right? And if if x is 3, 3 can always go back to itself, right? Then there's no way that I plus 1 equals to 0, right? But if x equals to 2, and then, so the next state is that x has to be 1, right? Then y will go to become 0. Okay, so now given y equals to 1, you have no idea what is happening, right? But so these two will lead to two different results, right? And then, so let's say if the previous state xi minus 1 is 3, then you know this guy will be 1 for sure. Therefore, this guy and this guy dependent, even if you know yi is 1, right? So that's not a Markov chain. That makes sense, right? The problem is that it's not one-to-one mapping. Okay, you kind of lose information. Okay, great. Yeah, so it's not Markov chain. Then what should we do, right? So let me write it. So it's not a Markov chain. Markov chain. No, in general. Okay. So basically, if it is not a Markov chain, then we cannot use the formula that we used before for Markov chain, right? But we still can use the formula we used before to compute y, right? So remember how we can compute y? I mean the entropy rate of y, right? So we can still do this. Yeah, we can still do this, right? There's no problem of that. So this gives my theorem as long as it is stationary. Oh, by the way, so let me say if x is stationary, then will y be stationary? Why?
Because the transition between the two doesn't have to be stationary. Like x itself can be stationary, but if the mapping from x to y1 or y2 isn't stationary.
No, it's not time dependent. Yeah, stationary means that just the transition probability is time dependent, right? So if the transition probability for x is not time dependent, then y is not, right? Yeah, so this is probability dependent on the past, right? But the probability distribution will not depend on the past. I mean, will not change. Okay, yeah, think about that. So y will be still stationary, okay? So then we can still use this formula to compute the entropy rate, right? There's no problem of it. Okay, entropy rate, yeah, it's better write it down. So let's say if x is stationary, then y is stationary, and the entropy rate exists, right? And you can compute that using this formula. Okay, very good. And do we have any problem to compute this? Or, in general, right? Let's say if we have a stationary process, we can use this formula to compute the entropy rate. But how we can do that? So basically, what do we do is that we compute this as a function of n, right? And let n go to infinity. But in general, so we have to compute that numerically, right? So we compute it, for different n, okay, until it converges. But the problem is that, do we know when it converges? Yeah, we just compute the difference, right? See that if the difference is very small, then we say it's converged, right? But how small is small? We don't know that, right? So the fundamental reason is that, so this guy is upper bounded by this guy, right? Yeah, so this is basically by, the proof condition 1, right? We know this guy is a non-increasing function as n goes to infinity, right? So this guy is upper bounded by this guy. Oh, y, right? It's upper bounded by this guy. Okay, and normally we can now know when this would be very close to this. Okay, so instead, what we're going to do is that, so if we know there's a lower bound on this, and the lower bound and upper bound will be the same when n goes to infinity, then we'll have a very clear idea when to stop, right? So basically, the next step is that we're going to compute lower bound on this and see how it looks like. Okay, so let's see how we can compute lower bound on that. So we have a lemma in the book. So this guy is lower bounded by this yn given yn minus 1, yn minus 2 up to y2 and x1. Okay, so is that intuitive? Right, so here basically the difference between this and that, we replace the last y1 by this x1, right? That's where we use this hidden Markov property. Okay, so let's show that to see whether it makes sense or not. Okay, yeah, the proof of that is very typical proof in information theory, right? So now basically what we do is that, right? So we change a condition here, right? So basically what we're going to do is to add something, back and then remove something, manipulate that, right? And get this term. Okay, so yeah, let's see how we can get it. Okay, so basically, let's write it down. So this guy is up to y2 x1, right? So now we're going to show a upper bound of it. Okay. And so basically, one thing we can do is that we can add this y1 back, right? So they're equal because y1 equals to a deterministic function of x1. Okay, so basically, add y1 here basically means that we do not know anything new, right? So the conditional entropy does not change, right? And then based on the Markovian property of xi, so basically what we can do is that we can add all the past x back, right? So x0, x minus 1 up to x minus k. Okay, we can add all of the past x back, right? Any questions so far? Because in our Markov, right, so adding all the past x doesn't matter because we know x1 here already, right? And then we can also add all the y back, right? y1, y0, y minus 1 up to y minus k, right? So we add all of those here. Okay, they're still the same because they are deterministic, yes?
Why do you say we know x1? How do we know x1?
Oh, I mean, x1 is here already in the beginning.
Yeah, but isn't it hidden? So how do we know x?
Oh, we assume.
We just assume.
Yeah, because given here means we know that.
Okay.
Yeah. So now it's just pure math, right? So yeah, we know it. We know that. Okay, very good. So now we have a bunch of random variable here, right? So we add all the y's here, and then so basically what we're going to do is that we get rid of all the x. Okay, then we have upper bound, right? Because we remove some condition, right? So then conditioning will reduce entropy, right? So now we do the opposite, right? We remove condition, then the entropy increase. Okay, so then we have y minus 1, y2, y0, y minus 1 up to y minus k. Okay, very good. So this is conditioning reduces entropy. Okay, and then so now we have this yn given a bunch of random variable here, right? So we have like n plus k minus 1 random variable here, right? So we're going to shift it to the front because it's stationary. So we use the stationary property. So we're going to shift it in the front. So let's say we have n plus k plus 1. So we shift k plus 1. And now we have n plus k, yn plus k minus 1 up to y1. Okay, we add n plus k everywhere. Okay, very good. So what does that tell you? Okay, so now let's see what are we getting here. So we show this term is less than or equal to this term. Sorry, bigger than, oh yeah, less than or equal to this term, right? What do we mean by that? It basically means that it's a monotonic increasing function, right? Or monotonic non-decreasing function, right? So very good. And from here, we can conclude that. So the original conditional entropy, which is given by this, yn minus 1 up to y2 x1. Okay, so this is the original entropy. That will be less than or equal to, so this guy, n plus k plus 1 given yn plus k up to y1, right? So this holds for any k, right? So we can safely let k go to infinity, right? And then what is that? So what does this equal to? Recognize it? So when k goes to infinity for fixed n, right? And this is basically the entropy rate, right? Yeah, so which is the same as this guy. Or just like this indices goes to infinity given all the paths, right? So here, same thing. This indices goes to infinity and given all the paths. Okay, so that's equal to that. So now, so this guy is upper bounded by this guy, right? So now we have upper bound. We have both upper and lower bound, right? Hence, so this guy is lower bounded by y2 x1 and upper bounded by this. Okay, so now we have both bound, okay, and then we can pretty much compute it, right? And know that, right? So this guy, yeah, as we said before, so equals to y2, y1, x1, right? You can see the difference between this and that would just be there's one more x1 here, okay? So now we're not exactly done yet, right? We have one last step, right? In order to compute this guy, we need to compute this and that, right? But we need to make sure this and that will converge to y. Okay, the difference between this and that will be the same, right? That is not hard to show. So basically, in the book, let's say the page 86 in our book. So we have a lemma there. So this lemma tells you that the difference between the upper and lower bound, y2 x1 minus, should be, so this is larger, right? So this minus that. Y minus 1 up to y2 x1. So the difference between these two as n goes to infinity becomes 0. Okay, and yeah, you can take a look at in the book how to prove that. It's yeah, the proof idea is as similar as what we covered before. So we need to show, okay, so it will converge somehow, right? And then it becomes 0. Okay, I think that'll be it for today. So in the next class, we'll talk about the AEP for stationary ergodic process. Thank you.